Good afternoon. So as I often like to do, I am going to make a quick little video about this review worksheet 7.1. So the idea is that these videos I'm going to make whenever we have supplemental material, or maybe we didn't get as far as I would have liked in class, or somebody had some questions that I wasn't able to answer, or perhaps that I just wanted to think about and then come back to later. So the idea is that we always want to have time to go over these videos, ask questions about them and things like that, and this one will be no different. So I'd like for y'all to review this worksheet that I'm going to go over right now. And we also have a regular little review. These are just a couple of points that I pulled from the book that I thought were most important. So if you go to the OneNote, the college trigonometry is what you should have on the syllabus, and the homepage should have that URL. And if you go over here to classes, we have 7.1 review and 7.1 review worksheet. So I'm just going to do this worksheet real quick, and then if you have any questions, you can ask me on Wednesday. All right, so let's get started. So we have the initial side and the terminal side, and you can go either direction. This first figure is just to show you what the initial and the terminal side are. We always want the initial side to correspond with the x-axis. That just helps us to understand what we're doing. Now, of course, if you're doing physics and things like that, your x-axis can change, and you can choose your coordinate systems the way you want. But for now, we're just going to assume a pretty standard setup that looks like this, where this is our x-axis and this is our y-axis. Okay, so if one revolution is one circle going all the way around is equal to 360, then what does that mean a half a revolution is equal to? Well, in this case, it would just be 360 divided by 2 is 180 degrees. A quarter revolution is going to be 360 divided by 4, which is 90. Now, these are important because these correspond to very specific angles here. So this angle, if we have the x-axis as our starting point, this is equal to 0 or 360, right? If you've got a full rotation, you're back where you started. Now, if you just go to here, well, this is 1/4 of the full rotation, which makes this 90 degrees. If you go here, this is half the rotation, which makes this 180 degrees. And here, this is 3/4 of a rotation, so 270 degrees. And then here brings us back to 360 degrees. So this 0, 360, 90, 180, 270 are very important angles to keep in mind. So these help us to determine the quadrants. So the quadrants are like this. The first quadrant is 0 to 90. The second is 90 to 180. The third is 180 to 270. And the fourth is 270 to back to 360. So if theta begins in the standard position, which is along the x-axis, in which quadrant do each of these lie? So 45, well, that's between 0 and 1, or 0 and 90, so that's going to be Q1. And 45 is half of 90, so that's actually going to look something like this, right? Just about halfway between 0 and 90. How about negative 210? Well, this one is going to be a little bit more complicated. So it's negative. Now, normally we define positive as moving this direction, which means we're going to move in this direction. So we're going to go negative 90, negative 180. Now, negative 270 would be up at the top, but we don't want to go that far. So this is going to be, let's see, 30 past negative 180. So it should look something like this. This should be negative 210. And this puts it in quadrant 2. Right, quadrant 1 is this one, quadrant 2 is this one. So how about 420 degrees? Well, in this case, we're going in the positive direction. So 420, we know that we're already going to go a full rotation, right? So that's essentially going 360. Okay, but we're not going to stop. So 420 minus 360 is going to be 60. So 60 lies between 0 and 90, but it's most of the way to 90. So it's going to be a little bit more than this 45 we have over here. So I'm thinking something looks kind of like this. So this would be 420 degrees. And that puts it square in quadrant 1. So a radian. Radian is defined such that when if you have a radius of r, when your arc length is equal to r, so your arc length is this s, so when this r, I'm going to use a different color here, when this r is equal to this s, that defines your theta, your angle, as 1 radian. So that's just the definition of radians. Now in this case, a full circle is how many radians? It's going to be equal to 2 pi radians. So the answer to this is going to be 2 pi. So this is 2 pi. But given that the radius could be anything, we get that their circumference is equal to 2 pi r. So this is our equation for circumference. So from this point, we can begin converting between radians and degrees. So 180 is half of a rotation in degrees, so that means it's going to be half of a rotation in radians. So 2 pi divided by 2, this is just going to give you pi radians. 360, that's a full rotation, and as we determined earlier, a full rotation is equal to 2 pi. 90 degrees, if we remember from earlier, that was a quarter rotation, so this is going to be 2 pi divided by 4 is equal to pi over 2. Now 45 degrees is half of 90, so we can make our lives a little bit easier and say that this is pi over 4. We just took this one from 90 degrees and divided it by 2. So 60, this is a little bit more difficult. So 60 degrees is 1/6 of 360 degrees. So what we're going to do is say 2 pi divided by 6 is equal to pi over 3. And we can do something pretty similar and say that 30 degrees is so 30 degrees is 1/12 of 360 degrees. So what we can do is 2 pi divided by 12 is equal to pi over 6. So in this case, we can say that we have this nice little conversion where 180 degrees is equal to pi, or 180 degrees divided by pi is equal to 1. So we'll do 56 degrees. So the way that we would want to do this is by, so for these two, we'll use these nice little conversions to help us convert from radians and degrees that are not quite so simple. With the ones we did earlier, because they were really nice fractions, it was very easy to do it. But in this case, we're going to have to use these ratios. So what we're going to do is we're going to set this up and say, okay, 56 degrees, we're going to say 180 degrees over pi is equal to 1. So this means that 56 degrees divided by some radian measurement also has to be equal to 1. So that's how we're going to set up our ratio. And if we do this, we get x times 180 degrees is equal to 56 degrees times pi. Solve for x, you get that x equals 56 degrees times pi divided by 180 degrees. And if you do this, you get 0.31 repeat pi. Similarly, we'll set them to do the same basic idea, or use the same basic idea, and we'll say that 7 pi over 3 over some measure of degree, we'll call this x degrees, is equal to, in this case, we're going to use the pi over 180 degrees. I'm going to solve for x again. So we'll say 180 degrees times 7 pi over 3 is equal to x times pi. So now we're just going to divide out the pi. So this says that x is equal to 180 times 7 thirds, which turns out to be 420 degrees. So the idea is all we need to do is use our ratio right here, 180 degrees over pi is equal to pi over 180 degrees is equal to 1, and set it up in such a way that we get things to cancel and we're left with only either degrees or radians. Okay, arc length. So if the arc length S is equals r, the radius, times the degree, where the degree is in radians. If at any point you have a situation where your degrees or your angle is measured in degrees, then you have to convert it to radians. Let's find some arc length. So what's the arc length of a circle? Or was the length of an arc of a circle with radius 2 meters subtended by a central angle of 0.25 radians. So in this case, r is equal to 2 meters and theta is equal to 1/4 radians. So S is just going to be r theta is equal to 2 divided by 4 is equal to 1/2 meters. How about the length of an area of a circle with radius 4 feet subtended by the central angle of 60 degrees? So in this case, r is equal to 4 feet and theta is equal to 60 degrees. But remember, we can't use this. The 60 degrees doesn't help us. So we need to figure out a way to convert that. And as it turns out, we actually already have this. It's pi over 3. So we'll rewrite this as pi over 3. In that case, this gives us that the arc length is equal to 4 times pi over 3 is equal to 4/3 pi. And that gives us our answer. So how about the area of a sector? So the area of a sector is defined as 1/2, or is equal to 1/2 r squared theta. So again, theta is an angle that must be measured in radians. So let's say that we have r equals 8 feet and theta is equal to 45 degrees. So this 45 doesn't actually help us. We need to go back and convert it. As it turns out, we've already done that, and that is pi over 4. So we'll just go ahead and use our equation where a is equal to 1/2 times 8 squared times pi over 4. And this is equal to 64 over 2 pi over 4, 64 over 8, 64 over 8 pi is just 8 pi. All right, so for this next one, I decided to go ahead and write it all out and then just go through it to save us a little bit of time. So a tire of radius 12 inches is traveling at 52 miles per hour. What is the angular speed in revolutions per minute? That's really important because we're going to have to do quite a bit of dimensional analysis in this, right? And dimensional analysis means just playing with our units. So we have a radius of 12 inches, which I'm going to go ahead and convert to feet, and 12 inches is just 1 foot. Now at the end, we'll see what happens if I decided not to do this. It actually doesn't change what we're supposed to do. This just makes the math a little bit easier. And we have a velocity of 52 miles per hour, which I'm going to write as 52 miles over 1 hour. So now I want to get the velocity in feet per minute. This minute, of course, comes from the fact that we're looking for revolutions per minute. So I'm going to write this as 52 miles per 1 hour is equal to 5,280 feet per 1 mile. And now the miles cancel out. And I'm left with just feet up top, but I need to get rid of the hours on bottom. So I'm now going to multiply this by 1 hour over 60 minutes. This leaves me with 4,576 feet per minute. Now, On the other page, the review page, we have that the velocity is equal to r times omega. Now, this thing right here is not w, it's a Greek letter called omega. And from this equation, we can solve for omega, where omega is v divided by r. So we're going to plug stuff in. If omega is equal to v divided by r, then it's equal to 4,576 feet per minute divided by, well, r is just 1 foot, so the feet cancel out. Now, what would have happened if you didn't convert the original radius into feet? Well, that's not a problem. It just means that you would need to take this 4,576 feet per minute and convert that into some number of inches per minute. Not a problem. The inches would still cancel out and you'd be in a good place. So you now have 4,576 radians per minute. That's what is left over. The feet are canceled, so the question is what is left up top? The answer is just radians. So radians per minute. And we know that 1 revolution is equal to 2 pi radians, right? We're looking for revolutions per minute. So we're going to do the same thing down here and have 4,576 radians per minute times 1 revolution over 2 pi radians. The radians cancel out, and we're left with just what is here in blue, which is revolutions and a minute, revolution top, minute on bottom, and you're left with 2,288 over pi revolutions per minute. If you wanted to, you could take that 2,288 and divide it by 3.14 or something like that to get an approximate solution. That would work. So the idea with this problem is that we had to do quite a bit of dimensional analysis, quite a bit of unit conversion. We had to choose if we wanted to leave our radius in feet or inches. Either way is perfectly fine. It just changes how we're going to do our velocity, if we want to convert our velocity even further into inches per minute or not. All right, so let's go ahead and make sure that we have all of our units and everything, because units are definitely going to be important. So we've got revolutions per minute down here, and that's what we were looking for. I like it. Go back up here. All right, the area we need to make sure that we have should be in feet squared, right? Okay, fantastic. And up here, the arc length should be in feet. And we've got meters here, good. We've got degrees, we've got radians, and it looks like we'll go ahead and put another degrees right here just to make sure it's obvious what we're doing. And looks like that's it. All right, so just check this out before class, or it's not due necessarily at any time. It's just good to be prepared if you have questions or if you want to go over something like that. That's not a problem. And I look forward to seeing you all for the first day of class.